Okay, so let's see what we got here. So centroid, right? So we got formula for centroids. So this is going to be just a matter of calculating. And let's see, we're looking at the region. We got a sphere of radius k. We're looking for the part where x is positive. Density is 1. Okay, so now there's 3 integrals. I claim that 2 of the integrals are going to be very, very similar to each other, and one of them is going to be different. Let me show you why. In fact, 2 of them are going to end up being 0, as it turns out, but then the other one won't be. So here's the picture. Let's see, how can I draw? So it's just, we've got just a hemisphere. It's just this there. There's nothing on the other side. Okay. Yeah. Okay. So the centroid, I want to appeal to your intuition. I claim that the centroid is going to be on the x-axis. So if you're doing an integral, one way, if you're doing an integral of y over this whole thing, or if you're doing an integral of z, there's going to be a turn. It's going to be the same thing. So algebraically, I claim that the computations of y bar and z bar are very similar. So I'm just going to do one of these. Is that cool? Yeah. Let's do y bar just for, no particular reason. So y bar is, let's see, 1 over m. In other words, 1 over the volume because the density is 1. Triple integral of y times density, which is 1, and then dv. By the way, the volume is 2/3 pi k cubed. Right? So I have 3 over 2 pi k squared. And then the triple integral. And now we've got to start worrying about bounds. So, yeah, you're right. There's this question of which order do you slice in. And off the top of my head, I don't know. I'm going to give it a shot. I'm not sure which way is going to work out. Maybe I'll write it down both ways. I claim there's sort of 2 different strategies we could take. I'm not clear in my mind which one's going to be better. So my first strategy that I'm going to take is let's look at the projection into the YZ plane. In other words, let's put dy and dz on the outside. Oops, sorry. There we go. So z goes from, let's see, this is a sphere of radius k, so negative k to k, and this is a negative radical to a radical. Usual stuff in there. And then what's the range of values for x? Well, x is going to go from 0, so for a given value of y and z, x is going to go from 0 out to the sphere, right? So you're going to have, let's see here, square root of k squared minus y squared minus z squared. And your integrand is y. So let's see if we can't sort of anticipate how bad is this integration going to be. Well, when I multiply, or when I do the antiderivative of y with respect to x, I'm going to get xy. This is going to get plugged in for x. So I'm going to have y times this square root. And that won't be too bad when I do a y antiderivative of it, because the y can play the role of, I can do sort of a, oh man, just dropped my pen. Let's write it down. We're going to get a bunch of stuff. This integral here is going to be y square root of k squared minus y squared minus z squared dy. And this is not a bad antiderivative.
Could you just push it up a bit?
Oh, yeah, I'm sorry. I keep forgetting. Yeah. So you just let u equal to this k squared minus y squared minus z squared. And then du is negative 2y dy. And I've got y dy right there. So that shouldn't be too bad. Now, as for the next step, let's see, off the top of my head, golly, let's see, there's going to be some expression involving z's. We're going to have an ugly expression involving z's that we're going to be doing an integral dz. But trig substitutions might do that. I'm not sure. You want me to work it out?
Yeah.
Yeah, why don't I work it out? I'm not entirely thrilled that this is how this is working out, so I'm going to want to do it the other way also. But let's see how this plays out here. So let's see. We've got okay. So we have a antiderivative of u to the 1/2, and then we have negative 1/2 du. So altogether we end up with, let's see, we have a negative 1/2. Then when I take the antiderivative of that, we get 2/3. So altogether I get negative 1/3 u to the 3/2. I believe. And into this expression we put y equals, let's see, negative square root of k squared minus z squared to positive square root of k squared minus z squared. Did I do this right? I think that's right. So I was working on this dy integral that the dy integral went from a negative square root to a square root. So the antiderivative here was this negative 1/3. This expression, the dz integral stays along for the ride. Plug in these values. Let's not forget the 3 over 2 pi k squared. Oh, conveniently that 1/3 and the 3 are going to cancel. So okay, so I get negative 1 over 2 pi k squared integral. Okay, now I got to plug these values in for this is going to actually be really nice. Oh, it's really nice. Oh, this is lovely. Oh, no, this is beautiful. You don't see it yet? Oh, it's it's 0.
Oh,
0, because when you take these two different y's, their squares are exactly the same. So when you plug in these two values and subtract, you're taking whatever this is and you're subtracting it from itself. So 0, you get 0.
That's the coordinate for the y.
Sorry?
That's the y coordinate for the.
Yeah, then that's y bar. That's right. And we knew that was true. We sort of knew just geometrically that the centroid was sort of supposed to be there, right? Yeah. Okay. Now let me just set up. If I were to do this sort of the other way, same problem. Oh, so same deal. Let's just set it up with slicing the other in a different way. Let's see, what's that fraction again? 3 over. Okay, yeah. 3 over 2 pi k cubed. Cubed. I wrote squared. I meant cubed. Embarrassing. That's cubed. Not that it matters, but still. And this time, let's take the point of view of, hey, this has got a, the slices perpendicular to the x-axis are not that bad. So let's look at dx on the outside. And then we'll do dy dz on the inside. So x goes from 0 to k. And the cross sections then, for a particular value, wherever you might happen to be, the cross sections are going to be just kind of disks like that. And those are going to be disks whose equations are y squared plus z squared is equal to k squared minus x squared. And let's see, how bad is this going to be? Is this going to get ugly? Let's take a shot. So z is going to go from negative square root of k squared minus x squared to positive square root of k squared minus x squared. And then y is going to go from negative square root of, let's see, k squared minus x squared minus z squared to positive square root of k squared minus x squared minus z squared. Again, my integrand is still y, Lovely. This is even better. Because when you look at this integral here, that inside integral, the antiderivative is y squared. You get the same thing when you plug in these 2 pounds. Subtract, you get 0. Boom. So sometimes ugly is actually pretty. Right? Yeah. Here the convenient 0 showed up faster. And it's hard to anticipate, which way. So one thing you might want to do is, when you write down something like this, the first way we attack this y bar, you write this down and you think, wow, that's this first integral. I mean, I can do that, substitution, etc. But let's just write it down the other way. Maybe we'll get lucky. Right? And there's an argument that says that as soon as you write that down, you should say, you know what? Let's do it this way. Maybe this is better. And that sure enough, it turns out that this one's easier. Does that make sense? Yeah. So let me look at the x integral. Let's see here. Okay. I'm going to sheet of paper. So this is going to be, and by the way, z bar, same, very similar thing. Very similar. So you can, you can figure out. Yeah. So, okay, x bar is, let's see, well, again, 1 over the volume, triple integral x dv. Again, you get to decide how you want to slice it. Note, it's still the same domain. The only thing that's different is we have a different integrand. So I can cheat. I don't have to go through this whole slicing process again. I could say, well, I could have this expression with an x there. That would give me an x squared when I do the antiderivative. Hey, that's cool. X squared, that's going to kill the square root. I'll just get a polynomial. That might not be so bad. We'll get some radicals will show up eventually, but that might be doable.
Could we try it that way, the second way we did, where the 0, it cancels 0 comes first? If we did the order we did,
I'm sorry. Yeah. So here was our two choices. Here was our two different ways that we did it. Yeah. I think I'm thinking it'll be better when we have x in these spots. I'm kind of liking this one better. Okay. Because then you get the x squared, and that kills the square root. If you have x here, this first antiderivative is xy, and you're plugging this in for y, and then you're going to have x times square roots. Which, again, you can do it with a substitution, but it's like, I don't know, it's just a little bit less desirable. So I'm kind of digging this one. Let's do that. So again, I'm going to cheat, recopy. It's 3 over 2 pi k cubed, integral from negative k to k. Integral from, well, I better write this out this time. This is negative square root of k squared minus z squared to positive square root k squared minus z squared, and then integral from 0 to square root of k squared minus y squared minus z squared, x this time, dx, dy, dz. Okay. Alrighty, so 1/2 x squared, we get 3 over, I'm going to pull out the half. Then I'm going to have x squared. I'm going to be plugging in this, and I'm just going to get plain old k squared minus y squared minus z squared dy dz. Is that cool?
Yes.
Okay. Y antiderivative. Okay, there's going to be some terms here. Yeah, I mean, look, you're going to have to do some trig integrals here in your final integral, your trig substitutions. This antiderivative is no problem, right? And you just have to plug in negative square root and square root, so you get. Well, let's see. You have. Wow, I'm trying to do too much in my head here. It's a bad habit of mine. K squared y minus 1/3 y cubed minus yz squared. Plug in for y, negative square root and square root. And these are odd powers of y. You're plugging in negative values so they don't cancel. They're going to double. That's right. And so you're going to get some square roots and some square roots times quadratics. But these are integrals that you've done for other problems, and the same techniques will work. Trig substitutions is the punchline. Yeah. So this one, yeah, you're going to have to actually get your hands dirty a little bit there and crank it out. Yeah. Is that cool? All right. Okay, cool. We'll stop the...